Hello, this is Jack Jackson. Today we're going to be looking at transformations in geometry. I'm going to start by showing you this thing here called Geometry Collected Resources. I've mentioned this in some earlier videos as well in my playlist, but I have collected and created a bunch of GeoGebra activities for doing lots of different things, but in this particular collection they're for doing geometry. I've organized them in chapters that sort of collections here, and these include the public, all of the public GeoGebra activities that I've made for geometry, along with several that I've collected from other really good sources, um, particularly the GeoGebra team and Tim Brzezinski and several others that are really good. And when we're specifically talking about transformations, this is this group 15 down here, and I've sort of subdivided this into translations, reflections, rotations, compositions and glide reflections, dilations, and then more transformations. And then what I want to show you now is one on more transformations called introducing transformations. This could be done at the beginning as an introduction, or it could be done as a summary as we go through this. So some of these different types of transformations, we have more detail of them and different ways of looking at them and other things here in the earlier collections up here, like just on translations or reflections, and then also in the earlier videos in some of my playlist here on transformations. You're going to want to open this thing in the app like this. Now, when you this could be viewed on even an iPhone or iPad or something, but it's really not formatted for that. It's formatted for a computer screen. So hopefully you've got a decent computer screen here. Okay, so we'll start with an introduction here. There are 5 basic types of isometries: the identity transformation, the translations, reflections, rotations, and glide reflections. And it turns out these are the only types of transformations of figures in the plane, points in the plane, that map a pre-image set of points to a congruent image, something that's the same size and shape, that preserves distance measures and angle measures and areas. We will introduce and explore each of these, and the composition of any 2 isometries turns out to be another isometries. We'll also explore dilations, which are size transformations that map a pre-image figure to a similar image figure. So we might say, same size, same shape, but different size. Compositions of isometries and dilations are the only transformations of points in the plane that map pre-images to similar images. So let's take these one at a time. We'll start with the identity. We can look at the geometric definition. The identity function maps every preimage point back to itself. This maps a preimage to a congruent and equal image. So if you look at this as the preimage point, set of points here, any triangle, and its image is exactly the same. B prime is B, A prime is A, C prime is C. So it's exactly the same set of points. In some sense, maybe that's a little bit boring or special transformation, but certainly it will do that. This is the only transformation that you actually get the exact same set of points. So this is the only way we would say these 2 figures are equal, is when they are exactly the same set of points. And notice that every point in the plane is a fixed point for the identity transformation. There's nothing to construct there. If you have coordinates for it, x prime is x and y prime is y. So x prime, y prime is x, y. There's do nothing with the formula. Okay, now let's go to something a little more challenging and interesting. Is translations. In a translation, what we do is we slide the figure along a vector, and so it's just sliding or scooting or shifting it around the plane. The technical term is a translation, and we can identify that um, this way by identifying the specific vector. So the vector from a preimage point to its image point is fixed for translation. So in other words, if we connect the preimage and image points, then the line segments that we get are congruent and parallel, and the paths are going the same direction, the same length, and the same direction. To specify a specific translation, we specify the given vector. We might write that as t sub that vector v. Now, it turns out that you can actually specify that in several different ways. Okay, and one way we can specify it is just by picking a point A prime. So, you know what? Actually, yeah, so let me go ahead and do this. Pick a point A prime. But once I pick that point, then that really specifies the vector from A to A prime. And then you slide B to B prime and C to C prime along the same vector. So these vectors here are considered the same vector if they have the same distance, the magnitude, the length, and also the same direction. That is the same, they make the same angle with the horizontal. So right at the moment, this is by the vector 6.52 comma negative 1.62. In other words, both points, all points, all the infinitely many points here are take pre-image to image by that. They go to the right 6.52 and down 1.62. Of course, this is all relative to some, coordinate grid, and axes if we to identify what we mean by horizontal and vertical. Okay, so that's what we have. Now it turns out though there's different ways that we can specify the vector. Okay, I'm going to show you at least three ways here. One is by just specifying the image point A prime. Perhaps that's the easiest way. We can also identify that vector by giving the component form or the magnitude and direction form. So basically this is showing you in motion what's happening with a translation. You're just sliding every single point along that same vector to get to the same place again. Show you that again. So it's just sliding along that vector to get to the image point. I could make that little thing sort of reset by clicking one of these. Okay, so notice that there are no fixed points for a translation. So again, no fixed points for translation. Every point is moved to another point along the same vector from pre-image to image point. Okay, how else can we look at this? We could specify the vector by component form. That is, you give it the change in x, delta x or dx here, and delta y or dy here. It can show the change in x and y, and I can control the change in x here, the change in y here. So here are the vectors. Here's the image, and this one controls the horizontal shift, and this one controls the vertical. So I can also just put in a number here. Now, if you have the zero vector, where we don't move it at all, we don't really call that one a translation. That's the identity transformation. Okay, but for here, if I leave delta y to be 0, notice that just changing the delta x gives you a vector, delta x and then 0. That's going to be a horizontal change. Whereas if I set this back to 0 and just change the y, we're doing a vertical change. Of course, you can change both x and y. So for example, if we're going to go to the right 2 and say down 1, that's going to give you that particular one. Of course, if we show the grid, you can see that every point here is moved to the right 2 and down 1. Okay. All right. We can also give a vector by magnitude and direction. So let's see here. Let's go 20 degrees, and let's go a distance of 5. Okay, so we're specifying this vector. So the length of this vector now is 5. So it's 5 units along this path. Whoops, just, yeah, that actually moves both the pre-image and the image when I grab the vector and move it around. Okay, so it's 5 units along this path, and 20 degrees is the angle with the horizontal. So again, if I show the grid, say I put this here, you can see that that angle it makes with the horizontal is 20 degrees. Now this could be positive, rotates put the angle in the counterclockwise direction. Negative goes in the other way. Instead of calling this negative 38, it's thinking of it as a positive 322. Same difference there. And so you can see this angle. Okay, and so that specifies the angle of that we're going, and then this specifies the length of the vector. So 8.5 is the length of all of these vectors. There it is in component form. Um, if it's 18 degrees with a distance of 8.5, then that turns out at least approximately as 8.08 to the right and 2.63 up. Okay, and so you can kind of see that there. So again, we can specify that by this. Okay, so how can we specify this? How can we do a transformation like this with the built-in transformation? So up here we have tools that allow us to do transformations, and here's the translate by vector. So if I have a vector identified, so first of all we might want to identify a vector. So let me put a point here and say a point here. And then we could go to this one right here and identify a vector. There's multiple ways we can do this. As you've seen, I can do it from sliders and different things. But let's just say we have this. Now we have a vector identified from this R2 to S2. We can click on this here and say, well, not that one, this one, and click on translate by vector here and pick a point and a vector, and that gives us an image point. And then we can continue, we can repeat that, translate point B by that vector, and then let's just do one more. Translate point C by that vector. And then I'm going to use the polygon tool to get not only the, hang on, before I do that, let me, okay, let's do this, get that out of the way. Okay, so I'll get not only the triangle, but also its interior this way. And there's our image. And see, it's based dynamically on this one. So notice every point was moved 1, 2, 3, 4 to the right and 1 up as we're looking at it here. And it is dynamic, so if I move these around, these points get moved around with it. Okay, so that's how you can use this. There are other ways. If you've defined a vector different ways, you can specify that vector and do the translate. You can actually do a translate command down here too as well. Uh, let me get rid of this. This vector is called W5. I should be able to say translate, say point A by W sub 5. Yeah, and so it does the same thing. See, it's going to the right, 1, 2, 3, 4, and up 1, 1, 2, 3, 4, and up 1. So that's the same vector there. See. So there's another way we can do it. So there's a variety of different ways you can go at using the built-in commands to work with translations. Now, one of the things that we might want to do is to be able to do constructions of these, maybe not in GeoGebra here, but say on a piece of paper. Okay, and so what you want to be able to do here is to do a compass and straight edge construction. So let me show you how that works. Okay, so this one is this is done by starting with a given preimage and a vector. So here the vector KL is our vector. Okay, I'm going to move it down here. Okay, so let's see if we can translate this by this figure. Okay, that's going to work pretty well. Okay, so I'm going to click on this next step. And the way this is going to work, it's going to use properties of parallelograms. Um, okay, so the next step is you figure out how long this is. Use your compass. Let's say put the pointing in at the beginning and the drawing in at this. Measure that, and then draw a circle centered at A here. So we want the image A prime to be this distance away from A, so it has to be on this circle. Next, what we do is we set our compass going from the start to start, that is from the K here to the A, set it to that distance. So take your pointy end, put it here, widen your compass out or close it as necessary to get this distance from K to L. Then just basically slide that compass so the pointy end sliding up to L, and now make a circle that was that radius centered at L. Okay. Now, really, you don't even have to make the full circle on either one of these. As long as you kind of know, well, this is going kind of this direction, you might make sort of this part of the circle here. Okay, and the same thing here, you don't necessarily need to make the full circle, just the part over here. Now, these circles will typically cross twice, okay, and so which one is going to be the point that we want? Well, you can kind of know that this is going to the right and up, so it's this one over here. Okay, so let's just go over that once again. So we start with a figure here. We have a vector. We take our compass and set it to the length of the vector, mark a circle centered at A. The image point A prime is going to be on that circle somewhere. Next, set the compass to go from K to A prime. Slide that compass to the end here so that it starts the center at L and mark. So start to start, finish to finish. These will cross two places, but the place is pretty obvious is the one over here where it's to the right and up in this particular case because we're going right and up. And so that point there will be our image point. Why does this work? Well, it's because we're generating a parallelogram here. How do we know it's a parallelogram? Well, earlier in the course, we proved that a quadrilateral with both pair of opposite sides congruent is a parallelogram. It's not the definition of a parallelogram, that's a property of parallelograms. So we've made sure, by the way we set our compass, that opposite sides of this parallelogram, A prime L, K, are congruent, therefore it is a parallelogram. And that makes these vectors here parallel and the same length, which makes them the same vector. And so A is going to be translated by the same amount as K is to L from A to A prime is the same vector. Now you just repeat the same thing for the other vertices. Okay, so we just do the same thing for B. Okay, take the distance from K to L, mark the circle at B. At least, again, we don't have to mark the whole circle if you've got a compass. We're just going over to the right and up a little bit. So it's if you just mark a, say the portion over in here, don't worry about this part over here. Next, we then set the compass to the length from K to B, slide that over and mark that where those cross. And really, we don't have to do the whole thing here. We just got to do enough of this to see where these cross, and there's B prime. Again, we don't have to to draw in the parallelogram, but I've drawn it in to show you why this works. Again, of course, this is dynamic. You can see how those things are changing here. So that's a radius of that circle, and of course that radius was set to be, that's a radial segment of that circle, and that side was set to be, this side was set to be the same length as that one. And originally the radial segment of the big circle, of this black circle, was this, and that was set to be the same length as this vector here. Okay, let's do the same thing for C prime. Okay, draw a circle or part of a circle centered from the length from K to L, and then take a length from K to C, center at L, crosses there, there's our vertex, and we've got that there. So now we have a parallelogram again, and that's the correct thing. Again, it's not necessary here to draw the parallelograms. It's not necessary to draw the full circles, just the right portion of circles. But you hopefully you understand why this works is because of properties of parallelograms. Now, once we have our vertices, then we just simply connect the vertices, the ones that are supposed to, and now we have our image there. Okay, and so that's how we can use a compass and straight edge. I do want to point out one thing you can do if you want. Notice that you're drawing a circle here centered at A. Later on, you're drawing a circle centered at B and a circle centered at C. And all three of those have the same radius. So if you want, and you can keep track of it, then you could make all three of those circles at the same time because they don't change radius. So you could make the three circles or portions of circles there up front, and then do each of the other circles, like in this case the purple one here for C prime. Okay, that's an optional thing. All right, the next thing I want to talk about is what if we have a coordinate grid? So let's show a coordinate grid, and let's say we start with what's called a lattice triangle, lattice polygon. And we want to use this to use the grid to help us see what's going on here. In this case, instead of having to, like, say, use compass and straight edge constructions, we can make use of the grid, particularly if we've got nice lattice points, that is integer coordinates, or where the grid intersects points for the vertices. And kind of the same way for the vector. So here we have a vector, whether it's written down here or if it's up here somewhere, we notice that the vector just goes across 1, 2, 3, 4, 5, 6, 7, 8 to the right and down 1. Well, we just do the same thing for every point. Every single point goes to 8 to the right, down 1. And of course, this is true for these particular ones. Okay, if I draw a vector here, and in general, it goes to right 1, 2, 3, 4, 5, 6, 7, 8, and down 1. So that's the same vector, whether it's there or here or here, or in fact any other place, right? So any other place that's on the figure, you're going to the right 8 and down 1. Whether that's a nice lattice point or something that's maybe not a lattice point like here. So it's the same vector all the way up and down that figure. So when you have the x and y vertical and horizontal changes on your vector or integers and your lattice points for your pre-image vertices, the grid's a really nice way to work on that. Well, that means that if we now impose an axis with this, that we can say something about algebraic formulas as well. Okay, and so if this is the vector hk, in this case h is 8, k is -1, write A and down 1. By the way, if I go to settings and say show the value of that, that's what it's going to show, 8 to the right and down 1. Of course, that can change here. Okay, but that's this one's actually controlled by point A. So now I'm to the, let's go, let's match this one. Take it to the right 9 and down 2. And then we just do the same for all the other ones. Do C, B. Okay, so if you've got a formula that is in say X and Y, okay. So let me just take something like we'll do it down here. Say Y equals X squared, for example. Okay, if we think of that as the pre-image point, the pre-image set figure, right, set of points. If I will want to translate that by the vector, say 9, -2, I take my formula and where the y was, I put y minus a -2, which is y plus 2, equals, and I have x squared, and I replace x by x minus 9. And if you look, that will take every corresponding point now and translate that by that vector, 9, -2. So you can see every pre-image point is shifted to the right 9 and down 2. Okay, and so that is a nice way of working with that, with a coordinate grid and formulas. Now, if you do it in parametric form, x is f of t and y is g of t, then you just put it x is f of t plus h and y is g of t plus k, and that will translate the original relation to a new relation translated by the vector hk. Notice in parametric form, you want to add h to the x coordinate, you actually add h to the x formula, and y, you want to add k to the y coordinate, you actually add k there. But up here in regular x and y relations, it's a little bit more complicated because you have to do the opposite. If you want to go by the vector hk, you have to replace x by x minus h and y by y minus k. Okay, let's so once again, what if we've just got let's see, let's hide some stuff here. What if we just have a let me get rid of this here. I don't need this anymore. What if I just have a figure and another figure, and it's translated, we can see here, but how can you tell it's translated? Well, you might be able to see that we can just slide this across here, but one of the ways you can see this is just to connect a pre-image and image point. And then what you should notice is those line segments that we have, if we put the arrows on the right end, become the same vector. They are the same length and parallel. So if you connect a pre-image to image point, that gives you the same length and parallel line segments. That gives you what we want here. Okay, it gives you a translation. You can see it's a translation. Okay, so let's now look at reflections. In a reflection, what we do is we have a pre-image point and we have a mirror line. And what we do is we reflect, okay, I've got that fixed now. So what do we do here? We want to take this and flip it over this line. So we have to take it into the third dimension now and pick it up out of the plane, flip it over. You could do this on a piece of paper by um, folding the paper on this line, tracing and unfolding it. And so this gives us the image over here. Okay. So what does it mean for this to be that image? What does that actually mean geometrically is going on? Well, a reflection is a mirror image over the mirror line. That mirror line is called the axis of reflection, or just the mirror line. And we do this in such a way that if we connect up a pre-image point to an image point, that line segment, in this case A to A prime or C to C prime or B to B prime, is perpendicularly bisected by this mirror line. So the distance from C to the line is the same as the distance from C prime to the line. And if we connect those across, that's a perpendicular. So that point is the midpoint from C, the line segment from C to C prime, and it is perpendicular there. And so that's the true for all of these. So if I just had an image and I didn't have the mirror line shown, and I wanted to know that these were reflections, one of the ways I could do that is actually just connect up pre-image to image with lines segments and notice, hey, wait a minute, all of these are parallel. And if you just find the midpoints of all of those and connect those up, that is the mirror line, and all those segments will have midpoints that are on that same mirror line. Well, which points are fixed? The only points that are fixed are points on the mirror line itself. So if you happen to have this go through the mirror line, then we know that that point there and this point here that are on the mirror line will end up being fixed points. Okay, so how can we construct this with a compass and straight edge? Well, we're going to make use of the properties of a rhombus. Somehow we have to find something that has a perpendicular bisector, and we know that the diagonals of a rhombus are perpendicular bisectors of each other. Okay, so first step is to go out and make a circle centered at A so that it touches this mirror line twice. Okay, I've gone about 3/4 of the way from where A to A prime is going to be. Doesn't matter, just as long as you make this touch twice and identify those 2 points. Okay, the next step, identify those 2 intersection points. Okay, and draw circles without changing your compass setting. So all 3 of these circles, the original one here that intersected twice, and then these 2 new ones, all have the same radius. So once you make this first one that intersects twice, take this point here, where at the intersection, make your compass pointing in there, the marking in at A, go ahead and mark that if you want there, and bring it around to the other side like this. Do the same thing, move your compass to the other end without changing the width of the compass. Keep the radius the same. Go here to A, mark your circle here that goes there. And if you notice these 2 circles that we did at the end, the last 2, will intersect in exactly 2 places. One will be A, the other will be the image A prime. Now, why does this work? Well, we've made sure that this orange figure you see here is a rhombus, right? Since we made all 3 of the circles have the same radius, the distance from A to this intersection point up here is the same as the distance from A to the intersection point down here. And then the next circle was the same, so that's the same radius here. So these 2 have the same distance, same radius. And this circle here had the same compass setting, same radius. So these 2 have the same length. So what do we know? We know that is a rhombus. Again, it's dynamic. It doesn't matter where we put point A. Right? It could be on this side. Doesn't matter. That is always going to be a rhombus. And what do we know about a rhombus? we know that the diagonals are perpendicular bisectors of each other. And see, one of the diagonals is along this mirror line. So the other diagonal must be perpendicularly bisected by that. And that's exactly what we mean for that to be a reflection. So that's the reason that works. Okay, now what? Well, just do the same thing for the other ones. Now notice that all three of those circles, all three of them, the original one had to touch this mirror line twice, and both of these had to have the same. Now we can reset it for B. It doesn't have to be maybe as big for B, but it still needs to go down here and touch the thing twice. But once we set it, the mirror line twice, but once we set this for B, the next two circles have to be the same radius. One centered at this point of intersection, the other centered at the other point of intersection. They'll intersect at these last two circles that you see them in orange here. These two will intersect at B, but also back at the image point B prime. And why, again, does that work? Because of the rhombus. Now, you don't have to draw the full circles. The initial circle, when you go back here, you just have to draw enough of the circle to see where it crosses these two. So maybe draw it from like here to here. That's fine. And then you don't necessarily have to draw the full circles here. I think it's useful to show where this part of the circle where they go from B to B prime, but really all you need is this little portion back in here. So if you know B prime is going to be over in this area, just draw a portion of it here, and then same way for this one down here, you could draw just a portion in here. Again, I think it's useful if you show all the way going from B to B prime at least, to go a little beyond that. Or you can draw the full circles, that's fine too. And it's not necessary for you to actually construct the rhombus, but it is, I think, necessary for you to understand why it would be a rhombus, and that is the reason why this whole thing works. So again, do the same thing for C. To get C prime, go here, find the two places where this crosses the mirror line without changing your compass. Mark circles centered at those two intersection points. They should go through C. They'll also go through C prime. Again, the three circles here don't have to have the same radius as the three circles for B, but going to B prime, all three of those circles have to have the same radius, and going from C to C prime, those have to have the same radius so that you make a rhombus there, and that gets you your images. Now, once you have your images for A prime, B prime, and C prime, just use your straight edge to connect those up and finish up your construction. Notice if you do have any points where the mirror line goes through the figure, those points should be fixed, so it gives you a little bit of a check in that case. Of course, it doesn't have to be here. So anytime you've got points here, notice that if they're on the mirror line, they'll be fixed. But if they're not on the mirror line, the image will be on the other side of the line. Okay, how about if we go to looking at a grid? Well, it turns out that it's a little complicated to look at what's going on with the grid, with a mirror line on the grid. However, if your mirror line happens to be vertical or horizontal, then it really is easy to see where we're going to go, because you can because your perpendiculars are going to be horizontal if your line is vertical. And so then we're just counting grid things here, right? So here to get A prime, notice that we're just going 1, 2, 3, 4, 5, 6, 7, 8 this way. So just continue 8 on the other side, and that gets us to here for A prime. And similarly, B is just 1 to the grid line, so it's 1 on the other side. There's B prime. And C goes 1, 2, 3, 4, 5. So you just go 5 there, and that gives you your image points. Okay, if this is over here, for example, now B is on this side, so B prime is going to be on the left side here. And again, once again, you can kind of check it by noticing the ones on the mirror line are the same. Now, what if you have a horizontal line? Very similar kind of thing happens. Okay, let's say we have that there. Okay, so again, this time the perpendiculars are going to be vertical lines if this mirror line is horizontal. So again, we're just counting squares. Go down one square to get the mirror line, so go down one more on the other side to get A prime. From B to the mirror line, you're just going up 2, so go up 2 more to get to B prime there. C, you're coming down 1, 2, 3, 4, 5, so go down 1, 2, 3, 4, 5, and so that gives you your image points there. So that's pretty easy. Also pretty easy, but a little bit harder perhaps, is looking at what happens. Let's turn these off for a second. If you've got a line with a slope of 1, in other words, it's 45 degrees with the horizontal. Let's make one, well, let's say like this. Okay, well, in this case, your perpendiculars are also going to go at, well, at negative 45 degrees or negative 1 slope. And so you're counting not the widths or heights of these squares, grid squares, but the diagonals. So here we're coming in the diagonal. Let's say do C to C prime. 1, 2, 3, 4 diagonals in. So you go 4 diagonals on the other side. 1, 2, 3, 4. So there's C prime. Here's B, it's just coming in 1, so we go there. So this one is coming in 1, 2, 3, 4 diagonals here, so 4 on the other side. Sometimes you do these, you may have a half. So look, this is 1.5, so that there's a half, 1.5. And so that gives you your image. Once again, if the pre-image happens to cross the axes, of course, you're going to have fixed points there. And a very similar thing happens is if your mirror line has a slope, yeah, there it goes, slope -1, no, not quite. There we go. So there's one with slope -1. So again, you can just count the diagonals to see what's happening there. Okay, what if we add axes to this and then try to put coordinates with this? It turns out that this can help give us some algebraic formulas that work out nicely. And a few of those are easy to see. If you start with the relation x and y, you replace x by minus x, then the graph will be reflected over the y-axis. So if you let's get rid of some of this stuff here. So if you want the axis to be the y-axis, let's take something like let's say we take x, oh, let's do this. Let's take x squared, let's take x cubed plus 2y equals 3. Okay, and let me put that over in the correct graphics 2 window. Okay, so we got that particular one. So if we take that expression there, okay, so hang on, let me start over with that. Let's try. Okay, x cubed plus 5x plus 5y equals 7. Okay, let's take that one. I want to copy that. Okay, I want to get that one graphed over here in Y2 in graphics window 2. So we have that one graphed. So if I want to reflect that one over the y-axis, what I have to do is just take the x, and where the x was, put parentheses, and in that parentheses put the opposite of x. And then that should be then now graphed so that it is a reflection over that y-axis. So this one here is the image when this one over here is the pre-image. So if I'm staying with my normal color scheme, I get that. If I were to take that same original formula and replace y by minus y, then that will reflect it over the uh, y-axis, or over the x-axis. Can you see that that one's a reflection of that one there? If I take my original relation and replace x by y and y by x, that's a reflection over the line here, y equals x. So let's get rid of, which one I want to get rid of? This one, I think. Let's get this triangle out of the way. I don't really care about it right now. So the black one here is a reflection of the this one over this line here. Okay, what if we want to reflect over this line here? Let's get rid of this one. So start with that one. Replace x by minus y in parentheses and y by minus x. I think this will work. Let's see here. Yep. See how that's a mirror image over that line. So certain ones can can be worked real nicely for reflections, particularly the same ones that were easy to do with the grid. Okay, but in general, that's a little bit harder to use the grid or the axes or formulas in general. Okay, if you just have this pre-image and image set, and you don't have the mirror line, you say, well, what is this? Well, one way you can find out is connect up pre-image to image point. Notice that those are parallel, but not necessarily the same length. We got parallel for translation as well, but they were the same length. Here we get parallel, not necessarily the same length. Then look at the perpendicular bisectors. They'll all be on the mirror line, or they all will be the mirror line. The midpoints will all be in a straight line. That is your mirror line. Okay, let's look at rotations next. Okay, so in a rotation, what we have is we're taking our original set, okay, of points, and we're having a center point here, and each point follows an arc of a circle, and it goes through a particular angle. So this angle right here is the specified angle. So the angle from pre-image to center to image has to be the same, and the distance, these two distances here from the pre-image to the center and image to the center are the same. Okay, so you got a little connect up pre-image and image segments here. you got a little isosceles triangle here, right? Because these are the same length, and that angle is the given angle. So, heck, for example, there it is for here, isosceles triangle here. That angle is there, and then here's the other one here. So if you just want to see the triangles, there are the three triangles. There's the circular arc paths there. Notice 75 degrees, 75 degrees, 75 degrees. Okay, and of course this is done with this. If you want to see it in motion, notice as we take this thing starting at 0, we can go this way. Notice a positive rotation takes you this direction, which is counterclockwise, whereas a negative rotation takes you in a positive direction. I've got the arcs kind of going the wrong way here. They should be, if it's a negative rotation, it actually would be, the arcs should be coming this way. But it's negative 124 degrees is equivalent to positive whatever 360 minus 124 is this way. Okay, so let's say 46 degrees. Let's go a little bit bigger. Let's say 66 degrees, 63 degrees. That's good. So what is the geometric definition? To specify a particular rotation, we identify a center point x and a rotational angle theta. R sub x theta is how we would do that. Notice we use m for reflection and r for rotation. Since we use r for rotation, we need another letter for reflection, which was m for mirror. The preimage point follows a circular path to the image point, so that the distance from the preimage to the center is the same as the distance from its image to the center. And the central angle AX excuse me, AX A prime is the rotational angle theta. Positive rotations are counterclockwise, negative rotations are clockwise. You can enter in this if you want to enter in radians. Like if we want to do an angle of 1 radian, we just delete that, and that will interpret that as 1 radian. It defaults to the degree symbol, so if we want to go 35 degrees, for example, we would do that. Or say, what if I want to do something like 65 degrees? Okay. The only fixed point is the center, right? If A was at the center, you would notice that as we do the rotation, it would never move, okay? But all other points get moved. They move along some circular path, right? An arc of a circular path. Okay, how about compass and straight edge constructions? Okay. All right, so we start with the center and an angle. So what we do is we set our compass at the center and then make it go through point A, our preimage. And we draw the circle, or at least enough to the circle to go the 65 degrees this way. Next, without changing the compass setting, okay, we construct an arc centered at the vertex V of the angle. So there should be an angle somewhere here. Let me see if I can find it. Yeah, it's part of this guy right here, if I can get down to him. Okay. Okay, here we are. Let's see if I can get this where we can see everything we need. Okay, so you're given an angle and a center. That's where we start. Okay, so we start with an angle and a center. In this case, it's 65 degrees. It is controlled by this, but I'm not assuming, let's say it's 75 right now. but it's just whatever it is, it's given to you. We don't necessarily have a protractor, we just have a compass and a straight edge. So anyway, we start by making a circle here. Without changing the center, go up here, the setting, okay, and mark a circle here. Okay, let's start this one over. Here we have our pre-image. We're given a center point here and an angle here. Okay, we may not know the size of the angle. That's fine. We just have it specified there as the picture. Okay, so what we do is we start by taking our compass and set it from the distance from the center to A, make a circle, or at least enough of a circle to show which direction we're going to go. So we have that. Then without changing the compass setting, we mark a circle centered at the vertex of that same radius. Actually, all that we really need is this arc of the circle going from this point on one side to another point on the other side. So notice those are going to be the same distance from here. Next, we take our compass and we set it to be the distance between those two intersection points. If we were to make a full circle here, notice it would be centered at one and go through the other. Okay. Actually, you probably just make a little small mark there just to make sure you've got the distance the same. So you don't really have to construct that circle. Then go down here, take a circle centered at A of that radius. Notice that that's going to intersect our original circle here in two places. One of those is going to be a rotation by this angle if it's in the positive direction, and the other one is going to give us the image point if the rotation is in the negative direction. So you have to just kind of figure that out just by looking at it. So if we're going in the positive direction, we're going around the circle, around this orange circle from this point to this one in a counterclockwise method. So just go in counterclockwise here to the nearest one. There's A prime. And so that identifies the correct one. If we were rotating in the negative direction, then this point over here would have been A prime. Okay? Now, just repeat the steps for the next one. So next one, we go from X to B, and really we need this circle. Actually, we just need the part of the circle. Just make sure we're going at least 75 degrees. So be, go a little extra, go out here somewhere, but you don't need all this part of the circle over here. Then centered with the same radius, mark a circle, or at least an arc of a circle, where it goes from the point of intersection here to the point of intersection there. I'd probably go just a little bit beyond that so you can make sure you can see that intersection point clearly. Then next, set your compass to be the distance between those 2 points. This circle here you don't necessarily have to draw, you just have to make sure your compass is at that size. And then draw this circle here centered at your pre-image point. And again, it's going to cross 2 points. One of those will be B prime for a positive rotation of that amount. The other one over here would be for a negative rotation. We're doing a positive rotation here, and so we're going to get this point down here. Repeat for the last point. So C, set your compass starting at the center X, go out to point C, make that arc, or at least enough of it to go your 75 degrees. Mark the center at V, mark an arc of the circle going from a point here to its image over here. Same distance there. Okay. Then figure out the distance across here and mark a circle there. Well, you don't actually have to mark that one. Mark the circle down here at that same radius, and where these two circles cross, again, one will give you a positive rotation for C prime, the other will give you a negative. We're wanting this one here, and so now we have this here. Now, why does this thing work? Well, it works because of the side-side-side triangle congruence theorem. Notice that when we made these two original circles, the two orange circles here and here were the same radius. So that made sure that the distance, say from V to D and V to D prime, the V from center X to C and X to C prime, those were all 4 congruent to each other. So we got 4 congruent line segments there. And then we also made sure when we were doing this that this circle here had the same radius as this distance from D to D prime as this one right here from D to D prime, where those intersection points there with the 2 sides of the angle and that original circle, or the copy of the original circle, has the same length as the distance from here. So by side, 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 these 2 triangles are congruent, and that makes this angle congruent, and it also makes C prime the same distance from the center of the rotation as C is, and it makes sure that angle is going to match the angle up here that we're given. That's exactly what makes that a rotation. And so there's our final image. Doing rotations with a coordinate grid is not usually extremely helpful. It's a little more complicated to see what's going on here with the rotation, but some rotations are easier. If that rotation uh, is 180 degrees, then that's easier to see. What happens here is just going to be on the other side from that. So if I were to connect up pre-image to image point, notice that they go through there. See, notice this one goes right 3 and down 1. This goes right 3 and down 1 here, and you're exactly on the other side there. This one goes right 2 and down 1, 2, 3, 4. Continue to go right 2 and down 4. You get to this image point down here. So if it's 180 degrees, then this will rotate very nicely. Okay, if it's 90 degrees, that's when it also is not hard to see, too hard to see here. Okay, so what's happening here is this is positive 90 degrees, so we want this to be a 90-degree angle. Well, since this is horizontal and this is vertical, that works out nicely, one distance here. Now this is a little harder here to see, but if you look at this, this goes 1, 2, 3 to the right and 1 down. To get to C prime, you go 3 down and 1 to the left. Okay, and so you can see that this has a slope of negative 1/3. This one has a slope of positive 3. So those slopes are opposite reciprocals. That gives you perpendicular lines. And so you can kind of use that a little bit to do that. If it's a negative 90, you can see it kind of going the other way, and you can use that to figure those out. Multiples of 90 degrees will work out. 270 also can work out. Let's see, 90. That's the same as negative 90. Yeah. Okay. So if they're multiples of 90 degrees, that can be helpful. So that means that if we add a axis to this, and if the center is at the origin, let me see if I can do that. Let me move this down a lot closer where we can see what we're dealing with. And we'll move the center to the origin there. Let's first look at 180 degrees. That one's the easiest. What happens here is, let's see, we take a point here. Notice the point 1, 4. goes to the point -1, -4. The point -2, let's see, let's go -3, 1 goes to 3, -1. So you're changing the sign on X and Y. Once again, 180 degrees. You connect that pre-image to image in a straight line. Those actually go through the center for the rotation of 180 degrees. Okay, if you're looking at 90 degrees, that one can be done as well. Okay, if you look here for B is the 0.14, B prime is -4, 1. Formulas are kind of backwards, so you end up replacing X by Y and Y by -X. And similarly, you can get one for -90 degrees there as well. Now, in general, it's much more complicated, but you can use some trigonometry to show that if you take a formula in general and you replace X by X times cosine of theta plus Y sine theta, and replace Y by -X sine of theta plus Y cosine theta, then that turns out to give you a rotated image by theta about the origin. That was a little more complicated. Going to leave that for another day to look at that. If you just start with these and say you don't know the center, and you connect up pre-image to image points, notice that these are not parallel, nor are they necessarily the same length. So they could be all different lengths, not parallel. So that's kind of interesting. That so in translations they were parallel the same length. Rotations they were or reflections they were parallel but not necessarily the same length. In this, in rotations they're neither parallel nor the same length. Well, it turns out though if you find the centers are not in a line, but their perpendicular bisectors do intersect at a point, and that point is the center point. And so once you've identified the center point, then you can identify the angle by one of the angles here. Say from A to the center to A prime, and now you've identified the angle and the center. You've identified it as a specific rotation. Okay, so it turns out those are the most basic ones: identity, translation, reflection, rotation. Turns out there's one more kind. It's called a glide reflection. And what happens on a glide reflection is you specify a vector and then a line that's parallel to that vector. And so what happens first is you slide the figure along the vector to do a translation. And then once you've translated it, then you have an intermediate image, which you then reflect over that line to get a reflection there, and that gets you to your final image. It turns out you can't do this with just one translation, reflection, rotation, so this is a different type of isometry, but it's really just built up out of two things that we've done earlier. Okay, so a glide reflection is a translation by vector followed by reflection about a line parallel to that vector. We specify the vector and the mirror line to specify the glide reflection. There are no fixed points in a glide reflection. If you want to do a compass and straight edge, just do the compass and straight edge for the translation first, then do it for the reflection. Okay. You can use a coordinate grid, but just use the same kind of things that we did before. If this is nice lattice points, again, to use the coordinate grid effectively, you're probably going to need that vector to be 45 degrees or vertical or horizontal there, or vertical, or at plus or minus 45 degrees there for the vector. I'm not going to talk about algebraic formulas. Okay. Okay, so if we have just the figures, so we don't have these vectors or this line, the mirror line at this point, we just have the pre-image figure and the image figure. We say, well, how did we get from one? Was it a reflection, a rotation? What was it? Okay. What we always do is connect up the pre-image to the image line segment. Now remember, let's review. If it's a translation, those would all be parallel and the same length. If it's a reflection, they're going to be parallel, but not necessarily the same length, but the perpendicular bisectors will all be the same. The midpoints will be in a line. If it's a rotation, they're neither parallel nor the same length, but if you do find the midpoints, they will not be in a straight line, but you can do their perpendicular bisectors. They will intersect at a single point, which is your center point. Okay. For a glide reflection, when we connect up the line segments from pre-image to image point, uh, they're not necessarily the same length. They're not necessarily parallel. Those things won't happen. But if you look at the midpoints, they will all be in a straight line. And once you have that, that will identify your mirror line. To finish it up, we just reflect the the uh, one of the figures. It doesn't really matter which. Let's say we reflect the final figure over the line to get the intermediate one, and then we connect up pre-image to image here. That vector will give us the vector. So now we've identified the vector and the mirror line for a glide reflection. It's interesting to notice that it really doesn't matter whether you do the glide or the flip, you know, the translation or the reflection first. You can slide it first and get this uh, translation to get the intermediate image and then reflect it. We could have also taken this same uh, uh, figure, reflected it over the line, and then translate it by that same vector, and we would end up at the same spot. So we get the same setting there. Notice that the perpendicular bisectors don't necessarily intersect like they do in a rotation, so we can't get this as a single rotation. Notice you got one, two, three different intersections instead of one single one, which would be your center if it was a rotation. It's not a rotation here. So this glide reflection is a new fifth type of figure. Finally, I want to look at one other type that's not a congruence transformation, but is a similarity transformation. It's called a dilation. In a dilation, you have a center point and a pre-image set, and in an image set, notice that the image is not congruent to the original, but it is similar. The angle measures are preserved. So this angle from A to C to B is the same as from A prime to C prime to B. Okay, and same for all the angles, but the distances are proportional. And this proportional factor is called the dilation factor. K is right now it's set at 2. So the way this thing is actually defined is you have your center point, you have your pre-images here. Okay, and to find the images, what you do is you make rays. So the rays are all centered at X. So we have these radial rays. They start at X, go through the pre-image point A, and somewhere on that ray will be the image A prime. Similarly, on this ray going from X to C, you will see C prime there, and similarly for B prime. Okay, well, how far out do you go? Well, there's where the dilation factor comes in. The distance from the center to A, you do K times that, in this case twice as much, will get you to A prime. Can you see that? You can probably, since it's just a factor of 2, you can probably see from X to A and from A to A prime are the same. So the distance from X to A, whatever that is, twice that will be the distance from X to A prime. And similarly for C and B. So it turns out that this is a size transformation, so it's the same basic shape but a different size. So you scaled it twice as big. Now, when I say twice as big, I'm really talking about lengths. So any other length that would be related to this, like the altitude or the lengths of the sides, are all twice as big as well. So the distance, say, from A to C, whatever that is, it's twice as much to get the distance from A prime to C prime. And this side here, C prime to B prime is twice the distance of this one here from C to B, and so forth for the other side. Angles, however, don't get distorted. They are the same. So the angle A here, CAB, is exactly the same size as the angle C prime, A prime, B prime. They have the same measure. They're congruent angles. Same way for C, angle C and angle B. C and C prime are congruent. Angle B and B prime are congruent. Areas, however, get multiplied by K square. So this area here is 4 times the area of this one here. You can kind of see that if I put it at the corner. Um, if we divided this up, we could get 4 of these little triangles. Split that one in half, and we get 4 triangles. Well, split it into thirds. There'd be 4 triangles that would be the same size as that one. Now notice if what points are fixed. The only fixed point is the center of the dilation. So if the center happens to be, say, one of the points on the figure, that particular point is fixed. Okay. Also notice, if the factor is bigger than 1, they will be in the order center, preimage, image. The image will be between, the preimage will be between the center and the image. But if you have a factor, and the figure will be bigger, right? Of course, if the factor is 1, that it's the identity mapping. If the factor is smaller, say 0.3 here, you will notice that if the factor is between 0 and 1, you get a smaller figure, and this time the preimage is, the image is between the center and the preimage. Okay. And so we're seeing that those if we sort of take those points and animate this, we'll see that those points are moving along those rays, but then also expanding out in distance there. Okay, and it's pretty clear to notice that if you just start with a image and the preimage and image there, if they're not the same size, you know a dilation is being involved here. And if it's just a dilation only, you should be able to connect up those preimage and image segments like that and trace them back to a common point. That's the center of that dilation. Now, in general, similarity transformations are found by compositions of isometries and a dilation. Might not just be a dilation by itself, but all similarity transformations can be figured out from there. Sometimes using a grid can be helpful. Once again, you want to just connect up preimage and image points here. Let me do this. Let me do it this way here. Give an example like this. So if you have your center is a nice lattice point, and you have lattice points for your preimage, and you have a whole number here, especially for your dilation factor, then it's pretty useful to use the grid. You just connect up center, and well, you don't even have to draw the radial lines here if you don't want to. Just notice to get to A, we go left 1 and down 1. So go left 1 and down 1 more to get to A prime. Here we went right 1, 2, 3, and up 1 for B. Go right 1, 2, 3, and up 1 more. This is if the factor is 2. If the factor was, let's say the factor is 3, you're just going to need to do that more than once. So to get to A, we went left 1, down 1. Do that 2 more times. Left 1, down 1, left 1, down 1. And for B, we're going right 3, up 1. Do it 2 more times. Right 3 and up 1. Right 3 and up 1. There's B prime. C is just going straight up. Straight up 2. We're going to go straight up 6. Will get you to C prime. Okay. So that can be useful. If we have axes on this thing, if that center happens to be at the origin, then we can work with formulas for this to make things work with us. So in algebraic formulas, in general, if you have a relation in x and y, and you want to dilate it about the origin by a factor k, replace x by x divided by k and y by y divided by k. I could show you some formulas here, but we'll come back and do that maybe in another video a little bit later dealing with the formulas. So, in conclusion, we have now kind of a long video here. I apologize for that, but we have gone over identity, translation, reflection, rotation, guide reflection, and dilation in one single video. We've looked at the geometric definitions, what are fixed points, how to do compass and straight edge constructions, how to use a coordinate grid if it's available, and if we have axes, talk a little bit about how to uh, find that. We talked about how to use to take an image and a pre-image, use the line segments to connect up points and their uh, from pre-image to image, and use those line segments to determine whether it's an identity, translation, reflection, rotation, glide reflection, or even a dilation. So this is a pretty good, pretty thorough introduction to transformations, all in one video. Again, this is much longer than I normally like to do a video, but hopefully got a lot done in this one thing.